All right, welcome everybody. So today we're going to be discussing equivalence relations. So we're going to continue with building basic mathematical concepts out of sets, and today we are on equivalence relations. So they are going to be very useful for us when we start creating other objects from previously built objects. I imagine many of you have seen equivalence relations before, but let's review them and see how we build them from scratch. Let's start with a few examples. What about a few examples? So, example. For instance, let's say if we have, we say that two triangles are congruent if their sides have the same sizes. Yeah, so there will be an equivalence relation. So we are saying it's a notion of equivalence between triangles. So the triangles, let's say they are represented by 3 points on the plane, on R square, right? So a triangle is represented by 1 point in R6, let's say, 3 points in R square. So we're saying that two triples of points are equivalent if the sizes are the same, right? So this is a notion of equivalence between triples of points in R2, and it has a meaning of the triangle is the same. Another one could be modulo. So we say that A is equivalent to B modulo 7 if A minus B is a multiple of 7, right? So that's an equivalence class, and if you're thinking of the numbers between 1 and 31, being equivalent means that you correspond to the same day of the week. So let's define a general notion that encapsulates all these notions of equivalence. So here is a definition. An equivalence relation is what? Is a relation, let's call it R. Let's put a name with field, so suppose the field is A. It's a relation R that satisfies the following properties, such that following properties: R is reflexive on A. So what does this mean? This means that for every x in A, x is related to x. So that's reflexive. Everybody is related to itself. I guess x related. This is just a shorthand right here for the notation the pair x comma x belongs to R. Okay, so that's what we mean by x Rx. It's easier to visualize when you have a binary relation to put the relation in the middle, but we mean that the pair belongs to the relation. Okay, so it needs to be reflexive. What else do we want from the relationship? The relation. We want that is, that's the wrong color. We want that R is symmetric. So that means what? That means that for every x comma y, if x is related to y, then y is related to x. Okay, so it's symmetric. If you one is related, if I'm related to you, you're related to me. So symmetric. What else? R is transitive, and that we said as for every x, y, and z, if x is related to y and y is related to z, then what? Then x is related to z, right? So transitive. So these three properties make an equivalence relation. So any relation that satisfies these is going to be an equivalence relation. Okay, let me ask you a question. Like the cousin relation. Remember we saw a few videos ago the cousin relation, two people that are related if they are cousins. Is that an equivalence relation? Okay, I'll leave that for later. Think about it. So right, the ones we have out there are definitely transitive. For instance, being congruent modulo 7 is transitive because everybody is related to itself, because a minus a is 0, is a multiple of 7. Is symmetric because if a minus b is a multiple of 7, then b minus a is also a multiple of 7. Is transitive because if you add two multiples of 7, then you get a multiple of 7. Try to work that one out and see if you can figure it out. In the case of the equivalence modulo 7, we know that if two things are equivalent, there is something representing that equivalent, which is if you divide over 7 and you take the remainder, you get the same thing, right? So the remainder modulo 7 of a number kind of represents everything that is equivalent to that remainder, right? Or the day of the week, for instance, if you're talking about days from 1 to 31, talking modulo 7, the days of the week represent everybody that is equivalent. Okay, so we would like to have that in general. Whenever you have an equivalence relation, to have something that an object that represents when two things are equivalent. We can define the equivalence classes of each element. So the equivalence classes are defined as follows. So if you're given an element x, so let's say given an element x that belongs to the domain of the relation, we define the equivalence class of x modulo r to be the set of all the y's in A such that x is related to y. Right, so this is called the equivalence class of x. So the equivalence class represents everybody that is equivalent to x and all its friends, all the ones that are like x. So for instance, in the congruence, in the example of the triangle, the equivalence class, one equivalence class corresponds to all the triangles that have the same size, exactly the same size. They all belong to the same equivalence class. And sometimes that's what we want to talk about. If you're talking about triangles, we don't care sometimes where they are located in the plane, like if it corresponds to the point 1, 1, 1, 3, 1, and 4, 2. Sometimes we don't care. We just care about talking about a triangle, and all we care is about the size of the triangle. So then essentially what we're talking about is the equivalence class among all the triangles in the plane corresponding to the particular size. So the equivalence class has the following property, and is that if you have an equivalence relation, x, the class of x modulo r is the same as the class of y modulo r if and only if x is related to y. Right? Because if x and y are related, they have exactly the same equivalence class. Whoever is related to x also equivalent to y, related to y, and vice versa. And conversely, if the class of x is the same as the class of y, well, then x belongs to the class of x, y belongs to the class of y, so they belong to each other's classes, so they must be equivalent. So the equivalence class is essentially a concrete object where now equality of equivalence classes corresponds to equivalence among the elements, right? It's going to be a very useful construct coming up soon. I let you guys try the proof of that lemma. It's a good exercise. Another way to visualize equivalence relations is using partitions. So let's define this. A partition of a set A is a set, let's put it a name, pi of subsets of A such that satisfying the following properties. Okay, so pi is a set of subsets of A. So it's a collection of subsets of A. So we have many subsets of A. And before writing out the properties, let's draw a little picture of what these things look like. Suppose here is our set A. A partition is going to be a bunch of sets that look like that. Like we're going to partition the set A into, let's say, a few regions. And here we're gonna have 1, 2, 3, 4, 5 different regions. So this could be a partition of A into 5 subsets. Okay, so that's what a partition is. You just break the set into different pieces. So to be a partition, what properties do we want to have? So first, any two elements of pi are disjoint. Any two sets that belong to pi are disjoint. Right? So you can see this in the picture. Any two of them are disjoint. And B, we want that every element belongs to somebody in the partition. Every element of A needs to be inside somebody in the partition. So we say that by saying that the union of the partition, so that meaning the union of all the sets that belong to the partition, has to be everything. Okay, so a partition is a bunch of subsets of A such that they are all, the intersection of any two of them is empty, but the union of everything, the union is everything. And that pretty much looks like a bunch of equivalence classes, right? So it's no difference than having, so on the one side, so assume R is an equivalence relation on a set A. Well then, how do we build from an equivalence relation the associated partition? We want to put all the elements that are equivalent inside a single subset of the partition and separate all the equivalence classes. Well, so that's exactly what we want. We want a set of all the equivalence classes. Then the set of all equivalence classes for X that belongs to A is a partition of A. Right, so essentially it's like we have our partition of, our equivalence class modulo 7 of the numbers from 1 to 31, and essentially we can partition the numbers from 1 to 31 by using the days of the week. So we put in one element of the partition all the Mondays, so there's all the numbers congruent to a 0, let's say, modulo 7. Then in another one we put all the Tuesdays, so that's all the 1 and the 8 and 15, all the ones congruent to 1 modulo 7. And we can partition the numbers from 1 to 31 in 7 subsets corresponding to each day of the week. So that would be a partition associated to the equivalence modulo 7. And also, if you're given a partition, we can build an equivalence class from it. If pi is a partition of A, we can define an equivalence class related to it. Right? This, like you can see in the picture right there, you imagine all the ones that belong to each piece, you make them equivalent to each other, and then you make so that the equivalence classes are exactly all the pieces. So we can define the set of all pairs x, y that belong to A square, such that how can we define the relation? So when do we know that two elements are equivalent using the partition? Well, we have to say that they belong to the same element of the partition. If and only if there exists a B that belongs to the partition, so this B is a subset of A, such that X belongs to B and Y belongs to B. Right, so two things are equivalent if they belong to the same thing. So the proof, the statement here is that if pi is a partition of A, then R is an equivalence relation on A. Okay, so in a sense, equivalence relations and partition are mathematically roughly the same objects. I mean, I guess sometimes the intuition you have for one or for the other is different and you want to use one or the other. But that's what an equivalence relation does. It partitions the whole domain into different equivalence classes. Okay? Pretty good. I'll leave you guys the proof of the theorem. Try it out and see what you guys think. So I want to make another important definition, which is the quotient. Okay, so how do we define the quotient? The quotient of A modulo R, where R is an equivalence relation on A, denoted A quotiented by R, is defined to be what? Nothing more than the corresponding partition, the set of all equivalence relations. Okay, so the associated partition is essentially called the quotient, but the quotient of a set modulo an equivalence relation is thought in a different way as a partition. So when we think of the quotients, now we think of each element, each equivalence class as a single thing, right? And now we have the elements of the quotient have the property that the two are equal, even only if they come from two things that are equivalent. So essentially, in the quotient, we are forcefully making equal things that on A were equivalent, right? So if you want to use equality instead of equivalence, we go to the quotient. So here is an example. Suppose that we have the following relation. So let's say for x and y in so we have two pairs of natural numbers, x0 and x1, and the other pair y0 and 1, and then we say that x0 x1 is related to related to y0 y1, and we're going to define them to be related if and only if the following happens. X0 plus y1 equals y0 plus x1. Okay, so this is a relation. So some points satisfy this, some pairs of elements of numbers satisfy this relation, some don't. It's not obvious at first glance that it is an equivalence relation. You have to prove the three properties: reflexivity, symmetric, and transitivity. One way to see there is an equivalence relation is to observe that this is exactly the case if and only if x0 minus x1 is equal to y0 minus y1. So essentially, two things are equivalent if the difference between them is the same number. So that's going to satisfy all the. It's easier to see that it satisfies the same properties, the equivalence relation properties once you have these. And now, what is the quotient? Suppose you believe me. Try it at home, proving all these properties. Suppose you believe me that if you take the natural number square modulo that R is an equivalence relation on the natural number square, when we take the quotient, what do we get? The quotient under this equivalence relation. Well, we're going to get all equivalence classes, right? So we are going to get the equivalence class of 0, 0. We are going to module over R of the pair 0, 0. We are going to get the equivalence class of 1 of the pair 1, 0. We are going to get the equivalence class of the pair 2, 1. Wait, this is the same equivalence class as 1, 0, right? 1 minus 0 is the same as 2 minus 1. So we don't want to add to this one because it's confusing. These two are exactly the same. So let's not put that one. What we do get is 2, 0. That's a different one. 2 minus 0 is not in the list yet. And we can also do 0, 1. and the difference is -1, and we can do 0, 2, and the difference is -2. So those are all equivalence classes. We can start to list them all and try to be different. What is can you guys see a pattern here? What is this going to look like? This quotient is a set of equivalence classes. How do we represent them? The idea that I want to just give you an idea, it's a hint for what something that is coming, is that this is more or less like the integers, right? Because you have, depending on whether the first one is greater or not than the second one, you might get a positive number or a negative number. So for instance, you might want to say, okay, look 0, 0 corresponds to 0, 1, 0 corresponds to 1 because it's 1 minus 0. 2, 0 corresponds to 2. The one that we tried, 2, 1, satisfies to is connected to 1 also, and 3, 2 also is equivalent, so related to 1. And 0, 1 right here is going to be associated to what? To -1. And 0, 2 is going to be associated to -2. Right? So in essence, the quotient n squared over r, it looks like the integers. Yeah. So we're gonna get to this. This is the way we're gonna define integers from the natural numbers later on. Okay, so that's how we use equivalence. That's how we use quotients. So we have an equivalence relation. We want to make them, the things that are equivalent, we want to make them equal. So we consider the quotient, and in there, things that are equivalent become equal now. One more thing I want to define. I want to define. Suppose we want to define a function on a quotient to some set B using a function that goes from f, that goes from A to B. Yeah. So suppose, for instance, that every day of the month, every number from 1 to 31, you have one particular thing you're gonna eat for dinner. I don't know. The first, you're gonna eat rice. On the second, you're gonna eat potatoes. On the third, you're gonna eat broccoli. You have a list for each day. You have a function that tells you what you're gonna eat that day. And you want to actually say, well, actually I wanna define a function that goes from the day of the week. Monday, rice. Tuesday, potato. Wednesday, broccoli. You can do this only if the original function had the same values on all the same days modulo 7, right? So in day 1, day 8, day 15, day 22, if on all those days you're eating the same thing, then you can say, well, now we have a function that goes from the day of the week to the food, right? But if on the 1 you're eating one thing and on the 8 you're eating another one, those correspond to the same day of the week. So you couldn't assign a function that goes from the day of the week to the food, right? So the same will happen here. So suppose that now that you want to define an area function for a triangle. And now you have a function that takes 3 points in the plane. So 3 points in R squared. So that means a point in R6 essentially. And gives you the area of the triangle limited by those 3 points. Can we quotient that and say and define a function that takes an equivalence class under congruence? So that means that takes the class of all triangles of the same size all over the plane and associates an area. Yes, we can, because whenever you have two congruent triangles, they have the same area. So it doesn't matter where they are in the plane, they're going to get the same area. So this function, the area function, can be defined on the quotient of all the triplets of points modulo the congruence relation on triangles. So in general, if you want to define a function that goes from the quotient to a set using a function from A, we need, what do we need? We need the function to be invariant under the equivalence relation. So we want to define a function using f such that f tilde of an equivalence class the equivalence class of R, right? This is an element of the quotient. So we want to define the quotient, the function of the quotient. So we have to say what it does on the elements of the quotient is equal to just what f does on the element x. Right, so that's very common that we want to do that. And I guess it's a lemma that says that such a function f hat exists if and only if we have the property that for every x and y in our domain A, you have that whenever x is related to y, their image is the same thing. F of x equals f of y. Okay, so suppose I'm going to give you an example and stop right there. An example for you guys to think. So consider R. So R is so let R be the similarity relation on R squared, the real squared triples. So okay, so we have three pairs, three points in the plane, and we say two of them are similar, are related if the angles of the triangle are the same. Okay, so angles. So what this means is that the angles in triangle are the same. So that's what it means for two triangles to be similar. It means that they have the same angles. And now we take 3 points in the plane. 3 points in the plane make a triangle. And then 3 other points in the plane, they make another triangle. And we say they are related by R if the triangles they define are similar. And now we want to define, to define an area function on the equivalence class of a triangle. Suppose a triangle has 3 points. Let's call it A, B, and C. It's a triangle. So A is a point in R2, B is a point in R2, and C is a point in R2. To the equivalence class of this one to be the area of the triangle ABC. Is this correct? Can we define an area function on the equivalence classes and their similarity? Is that going to work? Okay, I'll let you guys think about that. See you guys next time.